Ever seen one of those radio schematics and thought, what in the world am I looking at? All those strange symbols and lines actually tell the whole story of how a radio works. In this video, we'll crack the code so that you can finally read a schematic without feeling lost. Today we're going to talk about one of the most important tools in radio restoration, the schematic diagram. At first glance, a schematic can look like a maze of lines and strange symbols. But once you learn how to read it, the schematic becomes a map that shows you exactly how the radio is designed to work and how to bring it back to life. That makes me think of Psalm 119:105, which says, "Your word is a lamp to my feet and a light to my path." Just like the schematic guides us through the circuitry of a radio, the Word of God guides us through life. Without it, we're left guessing, trying to figure things out on our own, and that usually leads to mistakes, frustration, and sometimes danger. But with it, the path becomes clear. You see, a schematic doesn't just show what's there, it shows the proper connections. Every tube, resistor, and capacitor is placed with purpose. If we ignore the schematic or misread it, we'll never get the radio working right. In the same way, God has given us His Word to show us the proper connections for our lives, how to live in a way that honors Him. Romans 15:4 says, "For everything that was written in the past was written to teach us, so that through the endurance taught in the Scriptures and the encouragement they provide, we might have hope." The Bible is more than just words on a page. It's God's design for how we're meant to live. And here's the beautiful part. When we follow His design, our lives come into harmony with His will, just like a restored radio comes back into tune with the station. So as we take a closer look at reading and understanding schematics today, let's remember, just as the schematic shows us the way to restore a radio, God's Word shows us the way to restoration in Christ. All right. Let's dive in and see how to make sense of these diagrams so that they become tools instead of mysteries. Imagine you've just opened up the back of an old radio. Wires, components, tubes, everything looks like a maze. It can be overwhelming. But what if you had a map that showed you exactly where each path goes and why? Well, that's what a schematic diagram is. It's the roadmap for your radio. It's simply a drawing that uses symbols to represent the parts inside the radio. Instead of showing where the parts sit physically, it shows how they're connected electrically. At first, the symbols look confusing, but the more you work with them, the more they start to feel familiar, and soon you'll recognize them instantly. When you find a schematic for an antique radio, if you're lucky, you may get more than just the schematic itself. Some diagrams are very simple, just the electrical drawing with a few notes about the design. Others can be much more detailed. They may include a parts list, giving you values and reference numbers. Many will have a tube layout diagram, showing which tube goes in which socket. Some include drawings of the top or bottom of the chassis so you can locate parts physically. You might also find instructions for alignment, how to adjust the radio for the best performance. Some may include a dial string diagram for replacing broken or missing dial string. Sometimes they note design changes from earlier production runs or service bulletins that clarify how to handle a known issue. Some will also include voltage and resistance readings. In short, these documents can be more than just a drawing. They can be a complete guide to understanding and servicing your radio. Most schematics are laid out in a logical flow. On the left side, you'll usually find the antenna and the tuning section. This is where the radio first receives the signal. From there, the signal travels into one or more RF or IF amplifier stages, which strengthen and refine it. Next comes the detector, which extracts the audio from the radio signal. After that, the signal flows into the audio amplifier stage, which boosts it to a level that can drive the speaker. And speaking of the speaker, you'll usually see that on the far right-hand side of the diagram. Below all of this, or sometimes off to the side, is the power supply section. Here's where the AC from the wall enters. It's rectified into DC, filtered by capacitors, and distributed as the B+ voltage to power the rest of the circuit. If you keep this general flow in mind, left to right for the signal path and bottom or side for the power, you'll always have a sense of where you are in the schematic. Now let's look at a real schematic to learn what some of the different symbols represent. As a bonus, we'll also trace a radio signal all the way from the antenna to the speaker. As we trace the signal through the radio, think of it as a journey with different stops along the way. Each stop or stage works on the signal to get rid of static, tune in the right station, and make the sound loud enough for you to hear. Our journey starts on the far left with the antenna symbol, where the radio wave first enters. In this example, the symbol represents a loop antenna. A loop antenna is built into the radio, sometimes looped around the inside of the case, and other times attached to the back. Some radios don't have a built-in antenna and instead require an external one, often called an aerial antenna. This type of antenna connects to the radio at a designated hookup point, usually found on the back of the set. Over the years, different schematic symbols were used to represent antennas, but these are some of the most common ones you'll run across when working with vintage radios. The antenna is simply a piece of metal that acts like a lightning rod for radio waves. A radio wave is a high-frequency carrier signal that carries the audio information, the talk show, the baseball game, or music that you want to hear. It rides on top of the carrier wave. When the invisible electromagnetic waves from a radio station reach the antenna, it converts them into a weak electrical signal. Now is a good time to mention the solid lines you see on the schematic. These lines represent the wires that connect the various components together. When two lines cross with a dot at the intersection, it means the wires are connected. If there's no dot, it usually means the wires are not connected. Another way to show that the wires aren't connected is illustrated here, where one wire appears to hop over the other. Now back to the signal. The weak electrical signal moves into the tuning circuit, where we select our station. Here we see the symbol for a variable or adjustable capacitor, also called a tuning capacitor. Two parallel lines with an arched arrow. By turning the knob on the front of the radio, the tuning capacitor adjusts the radio to different frequencies. Connected to it is another type of variable capacitor called a trimmer capacitor, two parallel lines with a straight arrow through them. This component is used to fine-tune and calibrate the tuning circuit. Finally, the tuning capacitor in this radio is grounded, shown by this symbol. This ground symbol usually indicates an isolated ground, while this one usually indicates chassis ground. From here, the selected radio frequency signal from the tuning capacitor is sent to the first tube. In this example, the tube is the RF amplifier. In the 1930s, when schematic symbols became standardized, tubes were shown with their components enclosed in a circle, as you see here. Inside the circle are the elements of that particular tube type. In this example, we see the filament or heater, the cathode, a control grid, a screen grid, a suppressor grid, and the plate. Occasionally, you'll come across a schematic where the tube's components are not enclosed in a circle. Also be aware that the components are not always arranged with the plate on top and the cathode or heater on the bottom. Sometimes they're laid out horizontally instead. However they're drawn, whether horizontal or vertical, with or without a circle, the symbols for the tube's components are generally shown in a fairly consistent way. On this radio schematic, you'll see numbers around the tube next to each component or the wire connected to it. These numbers correspond to the tube's pins. If a schematic doesn't include pin numbers, you can always find them on the data sheet for that specific tube. Knowing the pin numbers is important for both restoration and troubleshooting. This tube amplifies the weak RF signal before sending it to the next tube. But before we follow the signal, there are a few more symbols to look at. The first is the squiggly line, which looks like a coiled piece of wire. And that's exactly what it is. It's a coil, also called an inductor, because it performs the electronic function of inductance. In this case, the schematic shows it as a wave trap. Notice the variable capacitor connected to it, with the other side grounded. While the tuning capacitor selects the frequency we want to hear, the wave trap is used to reject strong interfering broadcast signals. The inductor and capacitor together form a tuned circuit that filters out or traps unwanted frequencies, directing them to ground and keeping them from reaching the radio's main circuits. Next, we see the symbol for a capacitor. On this schematic, the capacitor's value is listed next to it. If a schematic doesn't show the value, you may find it in the parts list or on the capacitor itself, which will also show the voltage rating. When replacing capacitors, be sure to use ones with the same or very close capacitance. The voltage rating indicates the maximum the capacitor can handle, so your replacement should be equal to or higher than the specified voltage. Another type of capacitor you'll find in a radio is the electrolytic capacitor. These have a much higher capacitance than a standard capacitor. Unlike a regular capacitor, which is non-polarized, meaning it has no positive or negative end, an electrolytic capacitor is polarized and must be installed in the circuit correctly. On our schematic, the capacitor is shown with the standard symbol for a fixed capacitor. A fixed capacitor has a specific value that does not change. Sometimes you'll see slight variations of this symbol that look like this. There are different symbols for other types of fixed, variable, and electrolytic capacitors, each with their own slight variations. Here are some of the most common ones you're likely to see. The next symbol to look at is this zigzag line. It represents a resistor. You'll usually find its value printed right next to it. That value, measured in ohms, might be written out as a full number, like 6,800 in this example. But sometimes it's written in shorthand with a letter, either a K or an M. The K stands for kilo, which means 1,000. So a resistor marked 22K would be 22,000 ohms. Now on older schematics, you might see an M instead of a K. Originally, M was used as a Roman numeral for 1,000. Later on, as electronics notation evolved, K came to mean 1,000 and M came to mean mega or million. So how can you tell which one your schematic is using? Well, here's a simple rule of thumb. Resistors with values over 20 million ohms were very rare in antique radios. So if you see a schematic showing values like 50M or 100M, that M probably means thousands, not millions. There are numerous capacitors and resistors throughout a radio circuit. Now our amplified RF signal enters the 12SA7 converter tube, also called the mixer tube. This tube has two inputs, one for the RF signal and one for the signal from the local oscillator. That leads us to our next symbol. Here's another coil. This one is the local oscillator, as indicated by its connection to a tuning capacitor and a trimmer capacitor. The tuning capacitor adjusts the oscillator's frequency. Notice the dotted line connecting this tuning capacitor to the previous one? This shows that the two are ganged together, meaning they're mounted on a single shaft. This allows the oscillator frequency to track the radio station frequency by turning just one tuning knob. Now both signals, the radio frequency signal and the local oscillator signal, enter the converter tube. This tube mixes these two signals together, creating new frequencies at the output of the tube. The difference between the two frequencies is the signal that is needed. In this radio, it's resonating at 456 kilohertz. As the signals leave the plate of the mixer tube, they travel to the first IF transformer. This circuit filters out most signals except those resonating at the 456 kHz. The transformer doesn't completely eliminate all other frequencies. Instead, it greatly reduces unwanted signals while passing the desired 456 kHz signal to its secondary coil. Any remaining unwanted signals will be further filtered as the signal moves through the radio. This signal leaves the secondary of the IF transformer and enters the grid of the IF amplifier tube, the second 12SK7. The IF amplifier further boosts the desired signal while continuing to reject unwanted frequencies. The signal now passes from the IF amplifier tube to the second IF transformer. Like the first, this transformer is tuned to the fixed IF and filters the signal from the second 12SK7. The transformer's secondary winding is where the signal splits, sending it to both the detector and audio stage and the volume control circuit. This brings us to a couple of more symbols. First is the potentiometer, which looks like the symbol for the resistor. That's because it is a type of resistor. But notice the arrow pointing to the center of the resistor. This indicates it's a potentiometer or variable resistor. In this case, it controls the volume by regulating how much of the audio signal reaches the grid of the detector audio amplifier tube, the 12SQ7 in our example. The stronger the signal sent to the grid, the louder the radio. The other symbol to note is within the 12SQ7 tube itself. We're already familiar with the symbols for the filament, cathode, grid, and plate. This is the triode portion of the tube, which acts as the first audio amplifier stage. Within the same tube, we also see symbols for two diode sections, which make up the detector portion. As the signal enters from the secondary of the second IF transformer, one diode separates the audio signal from the IF carrier wave, a process called demodulation. The other diode generates negative voltages used to control the gain of earlier amplified stages, keeping the radio's volume relatively constant. This is called automatic volume control, or AVC. After demodulation, the weak audio signal is taken from the detector and amplified in the triode portion of the tube. This amplification boosts the signal to a level strong enough to drive the next tube, the output tube. The audio signal leaves the plate of the detector amplifier tube, passes through a coupler capacitor to block DC voltage, and enters the grid of the 35L6 GT power amplifier tube. This is the final audio stage, whose purpose is to increase the audio signal's power so it can drive the loudspeaker. The signal travels from the power output tube's plate to the primary winding of the output transformer, which is what this symbol represents. You'll recognize the two coil windings as the primary and secondary. What's new here are the three lines between the windings, which indicate that the transformer has an iron core. The high voltage, low current AC signal flowing through the primary coil creates a fluctuating magnetic field in the transformer's iron core. This magnetic flux induces a new low voltage, high current AC signal in the secondary coil. The transformed signal then travels from the secondary coil to the speaker's voice coil. This is the symbol for a permanent magnet speaker. And this is the symbol for an electromagnetic speaker. You'll see variations of both symbols. Permanent magnet speakers began appearing in radios in the early 1930s, but didn't become standard until after World War II. Before that, radios mostly used electromagnetic speakers, which generated their magnetic field with a coil connected to the radio's power supply. The current flowing through the voice coil creates an electromagnetic field that interacts with a permanent magnet, or a magnet field generated by a field coil. This causes the coil to move back and forth, vibrating the attached paper cone. As the cone moves, it pushes and pulls on the air, creating pressure waves that reach the listener's ear as audible sound. So that's a simple look at the signal's journey through a radio, and along the way we've learned about many of the symbols we'll find on a schematic. To explore more symbols, let's take a quick look at the radio's power supply. Let's start with a radio that has a power transformer. In this example, the power process begins when AC voltage from the wall outlet enters the radio's power plug. The first symbol we see is the power plug. Sometimes instead of a plug, you may just see two lines coming in. One of the incoming AC wires passes through a switch. This switch controls the flow of power to the primary windings of the power transformer, effectively turning the radio on and off. This is a single pole, single throw switch, but here are some others you may run across. This schematic shows two capacitors connected in series across the incoming AC lines, with the center point connected to ground. These are line filter capacitors designed to suppress radio frequency interference that can enter the radio from the power lines or exit the radio and affect other devices. For safety, these should be replaced with modern safety-rated capacitors, typically X1, Y2 types. Original paper or molded paper capacitors are prone to failure and can be hazardous. X1, Y2 capacitors are designed to fail open rather than short, helping prevent dangerous situations. The AC voltage enters the primary winding of the power transformer, creating a constant changing magnetic field in the iron core. This magnetic field induces AC voltages into the secondary windings. In this example, there are three separate secondary windings, each providing a different AC voltage for specific components in the radio. The first winding provides a low voltage to heat the filament of the 5Y4 rectifier tube. This tube is a full wave rectifier, as indicated by its two diodes. A half wave rectifier, by contrast, would have only one diode. Next is the winding that produces the high voltage DC, known as the B+. This DC voltage powers the tube plates. The winding has two outer terminals and a center tap, with the full AC voltage appearing across the two outer terminals. Each plate conducts during 1/2 cycle of the AC waveform, converting AC into a pulsating DC output. This pulsating DC is then filtered by the field coil and electrolytic capacitors, smoothing it into a more stable voltage suitable for the tubes. The smooth DC is distributed to the plates and screens of the other tubes, sometimes with additional filtering components to further reduce hum and noise. This is the symbol for the field coil. In addition to filtering the pulsating DC voltage, the field coil also serves as the speaker's electromagnet. We briefly mentioned electrolytic capacitors earlier. They're found almost exclusively in the power supply section, where they filter and smooth the DC voltage needed by the tubes. They work by storing charge when the voltage is high and releasing it when the voltage drops, effectively filling in the valleys of the waveform. Unlike the film capacitors you will use in restoration, the electrolytics are polarized, meaning they have a positive terminal and a negative terminal. They must be placed into the circuit the correct way, or they will fail catastrophically. Sometimes the schematic will indicate which side of the electrolytic is positive and which is negative, but not always. If it's not clear, a good rule of thumb is look at the center tap of the secondary winding that produces the B+ voltage. One side of the electrolytic will connect to this center tap, and that side is the negative terminal. The third winding in our example provides the low AC voltage needed to heat the filaments of all the tubes, except the rectifier tube. This voltage supplies the necessary heat to the cathodes of each tube. Notice that the winding doesn't directly connect to the tube filaments. Instead, one side connects to ground, while the other side is shown as a short arrow. You'll also see the same small arrow next to each tube filament. This shorthand indicates the heater connection point and was used to simplify schematics, avoiding the clutter of drawing multiple lines from the heater winding to every tube filament. That covers many of the symbols you'll find in a typical transformer type power supply. Now let's take a look at an AC-DC design that eliminates the need for the expensive and bulky power transformer. In this design, you'll notice a line with several spikes. The spikes represent the tube filaments connected in series. This schematic labels each filament with its corresponding tube designation. In an AC-DC radio, the filaments receive their power directly from the wall outlet. Another symbol we haven't seen yet is the pilot light, also called the dial lamp. Its main purpose is to illuminate the dial so that the user can see the radio frequency display in the dark. Most radios include one or more small incandescent bulbs for this purpose. The B+ voltage for the plates and screens of the tube is generated separately from the filament string. In this case, it comes from a half-wave rectifier tube with the pulsating DC filtered and smoothed by components, including this group of electrolytic capacitors. This line represents the negative pole of the capacitors, which are connected to ground. Notice the dotted line around the three capacitors. This indicates they are housed in the same enclosure. This could be a single metal can mounted on top of the chassis, or a cardboard tube housing the capacitors under the chassis. A few other schematic symbols that we haven't mentioned, but which you may encounter, include a rectifier or diode, a one-cell or A battery, a two-cell or B battery, a tapped resistor or voltage divider, and a fuse. Learning to read schematics is one of the most valuable skills you can develop in radio restoration. It transforms you from someone who just replaces obviously bad parts to someone who truly understands what they're working on. A schematic is your roadmap to successful restoration. It shows you not just what's connected to what, but why it's connected that way. It reveals the designer's intent and helps you maintain that original vision. I hope you found this video helpful. Please give it a thumbs up and please subscribe. Thanks for watching the Old Radio Revival, and I'll see you in the next one.